In this third lesson, we will address on the fault analysis perspective, a review on this. Also that includes the sequence component, or commonly called also the fault analysis using different sequence components. Now, in this we will cover the sequence component aspects. All the three, we will introduce all the three sequence components, positive, negative and zero sequence component. We will learn how to calculate sequence components from the phase components, and also we will see how the sequence diagram can be drawn, and then from there you can say that how you can analyze the different faults that we call short circuit analysis and so, and how this will be beneficial in understanding the different numerical relay principle, including different relay settings also. So, why in this lesson we are emphasizing on the symmetrical components or so called sequence component? There are two main important reasons that if you go with the phase quantities, then fault analysis for a large system becomes tedious, very complex, and symmetrical components analysis is being used as a tool to simplify the analysis process, so that different faults in a system can be analyzed, and in particular the unbalanced fault which is commonly found in the power system. Further, it is found that most of the numerical relays today use symmetrical components for decision making process, and also as I mentioned that such fault analysis is a very useful also while considering the circuit breaker rating or different relay settings in the system. Now, let us come to different symmetrical components. Any unbalanced set of phasors in a three phase system can be resolved into three balanced phasors that we call symmetrical components. These symmetrical components or the balanced phasors are three types: positive, negative and zero sequence. So, coming to the positive sequence, it consists of three equal phasors, equal in magnitude and with a phase separation of 120 degree each other, and it maintains the original phase sequence of the system. Like here we see here these three components of the positive sequence phasors VA1, VB1 and VC1. They are having same magnitude, separated by 120 degree each other, and the phase sequence here in this case VB1 follows VA1 and then VC1 follows VB1. So, therefore, the phase sequence is ABC, and that you can say that this phase sequence is that of the same as the phase sequence of the system. Furthermore, if you see here the magnitude of each phasor being same and they are 120 degree apart. So, if you can write down VB1 in terms of VA1, then VA1 120 degree, another 120 degree. So, that you can say that we reach to the VB1. So, that means that the VB1 can be expressed in terms of, you can say that alpha square VA1, where alpha is 1 with an angle of 120 degree, and similarly VC1 when we are representing in terms of VA1, then VA1 if you can say that proceed by 120 degree we reach to VC1. So, VC1 equals to alpha with 120 degree. So, that you can say that we can express VB1 and VC1 in terms of VA1 with the operating parameter alpha that equals to 1 with an angle of 120 degree. The 1 here in this you can say that representation corresponds to positive sequence component. Similarly, for the negative sequence component, it consists of again 3 phasors having same magnitude 120 degree separated, but here you can say that the phase sequence begin opposite to the that of the phase sequence of the system. So, it is in opposite to the positive sequence what we saw earlier. So, in this case you see here VA2 corresponds to the 2 here corresponds to negative sequence, VA2 corresponds to negative sequence component of phase A, BB2 corresponds to that of the phase B, and the negative sequence for phase C is BC2. Now, if you see here with here also it is 120 degree they maintain, they are having same magnitude, and the phase sequence if you see here this is nothing but ACB, whereas the system phase sequence is still you can say that ABC. And if we represent the VB2 and VC2 in terms of VA2, so then we see here VA2 120 degree proceed, we get VB2. So, therefore, VB2 equals to alpha VA2 and VC2 equals to alpha square VA2 with alpha being 1 with an angle of 120 degree. Now, next you can say that we will go to the zero sequence. This is something different. So, it consists of 3 phasors, equal phasors, and they are considered equal in magnitude, and they consider that maintain you can say that 0 phase displacement, that is no rotational sequence. So, therefore, no rotational sequence, that implies 0 sequence, and here you can say that we see here VA 0 equals to BB 0 equals to BC 0. So, in summary we see that you can say that the symmetrical components positive, negative and 0 we can summarize here like this, that in positive sequence you can say that BB 1 equals to alpha square VA 1 and BC 1 equals to alpha VA 1, and in case of negative sequence VB 2 equals to alpha VA 2 and BC 2 equals to alpha VA 2. So, if you see the sequence you can say that component sequence you can say that here it is ABC, here it is ACB, and here you can say that there is no sequence among the zero sequence component. Now, in this perspective we see that that any 3 phasors VA, VB, BC can be decomposed into 3 sets of positive sequence, negative sequence and zero sequence phasors. Note that in case of positive sequence each component VA1, VB1, BC1 are having the same magnitude, and similarly in case of negative sequence also, and so also in the zero sequence. But important point is that it is not necessary that VA1 magnitude and VA2 magnitude will be they will be same, or VA2 magnitude and VA0 magnitude will be same. It depends upon the magnitude of each sequence, that component here in this positive or negative or zero sequence component depends upon the different situations in the power system. Now, in addition to that, the other important aspect is each of the original unbalanced phasors is the summation of its sequence component. What we mean by that? That if we have VA in the for the system, VA corresponds to VA, VB, BC, VA, VB, BC you can say that. So, phase A you can say that voltage that can be considered summation of VA naught, VA 1 and VA 2. So, that you can say that we mean to say that if you see here, if this is you can say that VA 1 taken from this positive sequence component and VA 2 taken from this from the negative sequence component VA 2, and then you can say that VA naught you can say that here. So, if you see you can say that in terms of magnitude and angle, if you substitute here, then summation of VA 1, VA 2 and VA naught, that you can say that gives us the VA. So, that is what we say here, that each phasor VA or VB and BC can be represented by consider is summation of their corresponding positive sequence, negative sequence and zero sequence component. So, similarly we can express you can say that VB in terms of VB naught, VB 1 and VB 2, but you know VB naught equals to VA and VA naught and VB 1 equals to alpha VA 1 and VB 2 can be is expressed being considered in terms of alpha VA 2, and similarly VC can be summation of VC naught, BC 1 and BC 2, and VA naught you can say that VA naught plus alpha VA 1 plus alpha V A 2 alpha square V A 2. So, this you can say that we see from that you can say that each unbalanced phasors V A, V B, V C can be represented in terms of you can say that positive, negative and summation of positive, negative and 0 sequence component for the corresponding sequence component. Now, from the above you can say that discussion we can write the V A, V B, V C like this in terms of V A naught, V A 1 and V A 2 only, and thereby I can say that this V A, V B, V C can be put into a matrix form, you can say that in terms of like this. So, where you can say that we have 1 1 1 1 alpha square alpha and 1 alpha alpha square with V A naught, V A 1 and V A 2, you can say that the 0 sequence, positive sequence and negative sequence component of the for the system. So, where you can say that we see alpha equals to 120 degree. Now, we see here this in the matrix notation we can put, you can say that V A B C equals to a matrix T into you can say that V A with the 0 1 2 corresponding to the 0 sequence, positive sequence and negative sequence component, where this T consider is nothing but you consider the corresponding this matrix 1 1 1 1 alpha square alpha and 1 alpha 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 square. This leads to consider that other way, from this you can say that matrix representation we can write you consider also that the V A the sequence component 0 1 2 is nothing but T inverse V A B C. So, that therefore, you can say that from this you can conclude that V A naught, V A 1, V A 2 can be considered expressed in terms of this T inverse, where the T inverse becomes 1/3 of you can say that 1 1 1 1 1 alpha alpha square 1 alpha square alpha and then you can say V A V C. So, if you see consider relation between this is T and this is T inverse. So, you see here consider there is a relation between these bit to T inverse and T inverse is nothing but the inverse of the this matrix you can say that the earlier one perspective. So, this from this we see that you can say that there is a clear relations between phase components to the sequence component, and also you can relate the sequence component to the phase component by multiplying the corresponding matrix into the system. So, now you can say that similarly you can say that we can express the corresponding currents in terms of sequence component for the phase component, or you can obtain the considered sequence component from the phase components using the same you can say that T and T inverse matrices. Now, let us consider take an example. So, calculate the sequence components for the given phase voltages for a system with ABCH phase sequence. So, phase sequence is given here ABC, and for that you can say that the corresponding V A voltage V A is 110 with an angle of 0 degree kilovolt, and V B corresponds becomes 88 you can say that with an angle of minus 100 degree kilovolt, and V C 80 you can say that with 170 degree kilovolt. So, you see here you can say that this is not a balanced situation, neither magnitude being same or nor you can say that the angle being maintained 110 degree each other. So, this unbalanced you can say that phase voltages you can say that we will like to consider find the corresponding sequence components for this one. For that sequence component we will multiply the corresponding matrix you can say that, and T matrix you can say that, and then T inverse matrix, and we will find the sequence component for that one. So, V A naught, V A 1, V A 2 as we have seen you can say that for the phase A 0 sequence, positive sequence and negative sequence component multiplying with T inverse 1/3 of 1 1 1 1 alpha alpha square 1 alpha square alpha, and then you can say that V A, V B, V C substitute here, then we will calculate you can say that multiplying this we get the corresponding the sequence component voltage to be 0 sequence becomes and V A 1 and similarly V A 2 becomes. Now, what you see here that for these unbalanced situations the magnitude of V A naught and V A 1 and V A 2 are different, and they have their own you can say that phasor position you can say that on the phasor diagram plot also. So, so this you can say that clearly shows that you can say that how to compute the corresponding sequence component from the phase quantities. In the next example we look into you can say that how a balance you can say that how the balance condition, balance loading condition you can say that and the what is the corresponding sequence component perspective. So, I A 100 with an angle of 0 degree, I B current 100 with an angle of minus 120 degree and IC 100 with an angle of 120 degree ampere. Now, this is clearly magnitude are same and they are 120 degree apart. So, this is a clear balanced load condition in a system. Now, if we calculate the as we did for the voltage earlier case. So, here you can say that we see here I A naught, I A 1, I A 2, the T inverse into I A B I C. So, then if we calculate I A naught, you can say that in this manner, then because all the 3 phasors are balanced, you see here like this. So, therefore, phasor sum of this one for I A naught, I A plus I B plus I C, that becomes 0 ampere. And similarly, consider that you see I A 1 becomes equal to 100 with an angle. I am saying that next is multiplying the alpha here 1 with an angle of 120 degree to the I B phasor, and then alpha square you can say that 1 with an angle of 240 and to the IC phasor. Then you get, you can say that this you can say that phasors to be 100 with an angle of 0 degree. So, this 100 with an angle of 0 degree, that is exactly same as that of the I A, that is what we observe here. And I A 2 you can say that becomes, if you say I A 3 you can say that 1/3 of you can say that this, you multiply this factor and then you can say that you add this, you can say that 3 components, then again we are getting 0 ampere. So, what we say is that from this one that the 0 sequence component and negative sequence components vanishes, no more, is not available, each one is not available, whereas the positive sequence component is same as that you can say that the I A phasor. So, what you conclude from this you can say that observation for a balanced condition, only positive sequence component remains and the other two are not available. Now, in the other way you can say that given the sequence component, we can calculate the phase quantities also using the T matrix. Calculate the line currents if the obtained sequence currents for a system with phase with ABC as phase sequence, given I A naught equals to 0 ampere, I A 1 equals to 6.2 with an angle of minus 30 degree and I A 2 equals to, you can say that 6.2 with an angle of 45 degree ampere. For this case you can say that we say I A, I B, I C, we can put the consider T matrix as we know, and then we substitute the consider this I A naught, I A 1 and I 2, and then you consider we calculate the corresponding I A, I B, I C. So, we get here consider I A equals to I B happens to be, and then you consider the I C becomes equals to. Now, let us consider that the next one we know, from the above we consider that we will learn how to calculate the sequence component from the phase quantities and how the phase quantities from the sequence quantity perspective. Now, I will go consider to the sequence consider impedances, from where you consider we will now next you consider we will able to sequence diagram, and this sequence diagram will be useful in the fault analysis as a tool to consider to the power engineering communities. Now, for V equals to I Z relation, as you know, in that case we say consider that the corresponding relations between the corresponding voltage, phase voltages and so corresponding phase currents and corresponding Z becomes the phase impedance and so. Similarly, when you go to the phase quantities in terms of for the voltage V sequence quantities and the corresponding sequence quantities current I, then the Z must be also in terms of the sequence component perspective. So, that you can say that gives us a platform that how to use the corresponding sequence component for the fault analysis purpose. See here you can say that this is a system where we have a source G 1 and G 2, they are connected by a network. This network is having you can say that two transformers in the left hand side one transformer, right hand side one transformer connected by a transmission line. Then let us consider that we focus now for the this transmission line, which we assume to be a transpose one. Then the for this you can say that transmission system, the Z matrix, the corresponding impedance matrix for the transmission system can be represented in terms of consider the self impedance of the line and the mutual impedance of line. So, this you can say that for phase A self impedance, phase A to B consider a mutual and phase A to C consider a mutual component. So, therefore, this comes out to a 3 cross 3 consider symmetrical matrix for this purpose. So, let us consider that for the L here corresponds to line. So, Z L ABC corresponds to you consider the 3 cross 3 matrix you consider for the ABC phases of the 3 phase transmission line. Consider a voltage you consider V23 between bus 2 and 3 at any instant of time, and the associated current is let us say flowing is IABC. So, this V23 voltage drop across the transmission line from bus 2 to 3 equals to Z, you can say that into the corresponding I. So, this is what we know, you can say that from the voltage current relation for any transmission line. Now, this you can say that we know that the ABC, you can say that component of the voltage can be expressed in terms of T into the sequence component 0, 1, 2, you can say that of that voltage. So, this you can say that we can write T B 0, 1, 2, and then you can say that we know the right hand side, you can say that Z L A B C into T into I 0, 1, 2, that further you can say that I A B C can be written in terms of the sequence component of the current while multiplying the T matrix as we have learned. So, therefore, you can say that now from this sequence the relation V 0, 1, 2, you can say that can be expressed in terms of T inverse Z A B C T, you can say that into I 0, 1, 2, and therefore, V 0, 1, 2, you can say that is nothing but we can write in terms of Z 0, 1, 2 into I 0, 1, 2, where you can say that the Z 0, 1, 2 is nothing but you can say that T inverse Z A B C into T. So, this gives us a platform that you can say that the sequence component of the transmission line can be computed from the, you can say that this transmission line impedance matrix multiplying T inverse and T as in this relation. So, going by this, you can say that it is being found that you can say that the corresponding sequence component becomes if you put the substitute value of T inverse and T and the also you can say that the corresponding Z matrix of the transmission system, then this comes out to be Z s plus 2 Z m 0 0 0 Z s minus Z m 0 and 0 0 Z s minus Z m. So, this you can say that we see here from this relation you can say that the 0 sequence becomes equals to you can say that Z 0 equals to Z s plus 2 Z m and Z 1 you can say that becomes this Z s minus Z m and Z 2 becomes equal to Z s minus Z m. So, these are you can say that the corresponding relations we are getting you can say that from this perspective. Now, coming to you can say that sequence you can say that impedance of transmission line. So, we say that you can say that the sequence impedance of transmission line having positive sequence, negative sequence and 0 sequence as we have seen in the earlier you can say that it is earlier slide. So, these can be represented in terms of you can say that Z 1 L 1 for positive and L for the line. Similarly, negative sequence component we can represent you can say in this fashion Z 2 2 for the negative sequence and L for the line, and 0 sequence you can say that Z 0 L for you can say that like this you can say that, and the associated current from this you can say that which is flowing through this individual component is nothing but I 1 for positive, I 2 for negative and I 0 for you can say that the negative sequence 0 sequence component in this case. So, these you can say that transmission system being passive. So, if we say that subject to you can say that positive sequence voltage or negative sequence voltage, they lead to you can say that same impedance, and therefore, you can say that Z 1 L equals to Z 2 L for the transmission line. 0 sequence component you can say that is associated the 0 sequence the corresponding 0 sequence current or applied voltage 0 sequence voltage, and in this case you can say that the flux becomes additive. Only you can say that the flux in case of positive sequence component or negative sequence becomes they becomes balance, being balanced you can say that the summation of current you can say that becomes 0, but here in case of 0 sequence component the current no more 0 and the flux you can say that associated flux becomes additive. So, therefore, 0 sequence component is higher than the Z 1 L or you can say that Z 2 L, and typically you can say that for a transmission system depending upon the configurations and so including double circuit line. So, it varies from 2 to 6 times you can say that of the positive sequence component. The next element in the system you can say that is we are considering a source you can say that side the synchronous machine. For synchronous machine also like you can say that we have 3 sequence components. So, positive sequence, negative sequence and 0 sequence. This is being the source you can say that we model it as a voltage source. So, therefore, you can say that in the positive sequence component you can say that we have this corresponding voltage and you can say that an impedance associated. So, this you can say that gives us you can say that the positive sequence you can say that perspective, and then you can say that in a negative sequence you can say that we simply put you can say in terms of the Z 2 S only, because we consider you can say that that generators you can say that produce balanced voltage. So, no you can say that negative sequence component or no 0 sequence component. So, for 0 I am say that negative sequence component or 0 sequence component we do not have any source voltages, only they are being represented by you can say that sequence impedance perspective. See Z1 as you can say that in this case represent you can say that can be represented in terms of subtransient, transient or synchronous reactance depending upon the period of observation in time frame, and that you can say that we say you can say that is nothing but because we are concerned with the relay design and decision making process, fast decision making process. So, therefore, this corresponding in our perspective we will consider Z1 as to be considered the subtransient reactance. The Z2 as you can say that consists of you can say that the subtransient component of the d axis and q axis, average of that, and zero sequence you can say that zero sequence current you can say that associated with that you can say that gives you can say that the corresponding zero sequence you can say that impedance perspective. Now, for the transformer you can say that similarly you can say that we have positive sequence and negative sequence component, and being this is passive you can say that the negative sequence and positive sequence components are in general same. Coming to the zero sequence components, this is different you can say that for this transformer case it depends upon the connections. If the connection you can say that star grounded both these sides. So, the zero sequence component you can say that finds a path to the you can say that to be flowing to the line to the ground in both these sides. So, therefore, you can say that the corresponding associated zero sequence impedance you can say that is being connected to you can say that to the line side, or you can say that to the line side in both the perspective. When it happens to be can say that an ungrounded you can say that star you can say that, then we say that because it does not find a path to the ground. So, therefore, you can say that the current the zero sequence current does not flow in the line, and that you can say that therefore, you can say that the right hand side here in this case is no more connected to the system in terms of that to the system. When it happens to be delta connected in one of these side, you can say that the sequence component you can say that flows, the sequence component flows you can say that in the transformer windings, and thereby you can say that there is no scope to consider that flow, you can say that current flowing zero sequence current flowing in the line side. Unlike you see here you can say that the phase component you can say that the three phase component you can say that I1, IB1, IC1 they become 0 you can say that, but in case of here you can say that IA0, IB0, IC0 they are become say that co-phasors. So, they can you can say that flow you can say that in the winding of the you can say that transformer. So, that leads to that there is a circulating current in the transformer now inside the winding, and therefore, you can say that this finds a path like this, and like this you can say that you can extend the idea you can say that to the other connections perspective also, delta connection or Y star connections. So, these were considered depending upon the connection of the considered transformer, the zero sequence impedance of the transformer is being incorporated in the system. Now, we will classify the faults, we will go to the classification of faults and they see the what is the sequence diagram and sequence network for that. This is a 3 phase, let us first consider a 3 phase system. So, the 3 phases are you can say that short circuited by fault resistance you can say that in this case. So, again you can say that this is a balance condition as you know. So, therefore, the corresponding current becomes also balanced you can say that like this you can say that with magnitude same and 120 degree apart. Now, if you find the corresponding sequence component 0, 1, 2 for the fault conditions, and then you multiply you can say that T inverse matrix like this to the phase component IA, IB and IC, then we see that you can say that the IA, IB, IC. So, we see here this zero sequence component becomes IA plus IB plus IC, that becomes 0, and similarly, the negative sequence component also becomes 0, and only consider the positive sequence component remains in this case. So, we see here you can say that IA1 F equals to nothing but the same as IA F, and this IA2 F and IA2 I naught F becomes because they become considered 0 in this case. That implies that the corresponding sequence network for 3 phase fault condition becomes nothing but only it contains you can say that positive sequence component, no more you can say that negative sequence, zero sequence. So, that is why it only contains you can say that a positive sequence diagram, and where you can say that we can analyze only the positive sequence current perspective. Extending this concept for the single phase to ground fault, let us say phase A to ground fault as shown here happens to be there through an fault resistance RF, and the IB and you can say that IC components are 0 in this case. So, if you go to you can say that to the sequence component here, multiply you can say that the same T inverse matrix to this one, and IB and IC being 0 you can say that you substitute IB IC to be 0 here. So, you see here you can say that the IAF naught you can say that in this case become 1 1 1. So, only this, and IA1 you can say that becomes this 1 alpha. So, only this you can say element is available, and negative sequence also only this element is available. So, this implies that you can say that IA1, IA2 and I0 for the fault condition, they become same, and there each one you can say that is nothing but 1/3 of the, you can say that the fault current, you can say that which is flowing to this, you can say that RF in this case. So, that leads to a situations that all the three components are, you can say that same, both magnitude and phase. So, therefore, they must be connected in series. So, positive sequence network, negative sequence network and zero sequence network, they are being, say that being connected in series, and you can say that the corresponding current becomes equal to that I 0 by 3. And so, therefore, you can say that this connection diagrams becomes this, and then you can say that we have, you can say that. Now, note that you can say that the corresponding zero sequence component, you can say that happens to be there both for all the three phases, and therefore, you can say that the corresponding zero sequence component, you can say that will be there to provide the, you can say that, to compensate for this one, you can say that this corresponding RF becomes equals to 3 into RF. So, this is what you can say that the corresponding sequence diagram for this. Phase to phase fault, you can say that similarly you can say that you can extend the idea, and in this case you can say that no more, you can say that a ground is involved, and so that IAP is 0 in this case, IB and IC, this is a BC type fault, but the corresponding sequence diagram we are shown, you can say that as per the relation, you can say that for the phase A, you can say that positive sequence, and phase B, phase A you can say that negative sequence component, they are connected, you can say that in parallel, you can say that as shown here, and they can say that in this case I1 fault, you can say that I am say that equals to minus of IA2 fault. The fourth category of fault, you can say that which the power system encounters, you can say double line to ground fault or double phase to ground fault, you can say that here you can say that phase B and phase C with grounded by fault resistance. In this case you can say that both positive, negative and zero sequence, they all are in parallel, and you see here you can say that the IA1 you can say that, and I1 equals to IA2 plus I0 in this case. So, this you can say that we see that different kinds of faults have, you can say that will having the connectivity, you can say that of the sequence diagram in terms of positive, negative, 0 and depending upon the availability. Now, coming to, you can say that the for any, you can say that system like this, you can say that if you like to analyze, you can say that then finally, you can say that we will get the corresponding zero sequence, negative sequence and positive sequence currents, voltages, you can say that at different points. But again going to the phase quantities, we can for the phase quantity can be computed from, you can say that the T matrix, you can say that multiply, you can say that the sequence component matrix perspective. So, from this above, you can say that we see that any, you can say that set of phasors VA, VB, BC or IA, IB, IC can be decomposed into 3 sequence components 0, 1, 2 correspondingly, and then you can say that also you can say that from the sequence component you can get the corresponding phase quantities, and also the sequence you can say that components of each, you can say that impedance of for the corresponding transmission line, transformer, you can say that, and generators we see, and for you can say that in the next one you can say that lesson we will see how you can say that we can draw the sequence diagram for the systems and use it for the fault analysis purpose, and how you can say that such you can say that sequence component in the system you can say that is being useful for really applications. Thank you.